we're going to measure things. We have to think a little bit about that process. And this can be a tricky thing because students struggle with this idea of measurement and with errors and those kinds of concepts. And I'll just introduce them here. And then when it comes time to us to do measurement and to do laboratories and to measure our errors, we'll review all these concepts at that point as well. Measurement has limits. When you measure something, the precision of your tool determines the precision of your measurement. Makes sense, huh? Think about measuring the height of someone using a yardstick or meter stick with varying degrees of graduation on it. And depending upon the precision of that meter stick, you could record the height of a person in different number of significant figures. And so this idea of significant figures is related completely to measurement. I want to be very upfront here in that in math, you oftentimes have numbers that come out of calculations with many, many decimal places. And that's because what you're doing there likely is just messing around with numbers. Here in science, we almost always are measuring something with a tool, and as a result, that measurement has a precision, and that precision then sets a limit on how many significant figures we can report and the precision of any number we calculate from our measurements, and we'll see that throughout the chemistry class. There are various places you could go to, probably on the internet, and get a nice set of rules for significant figures, and we'll explore that in class. Heck, you can do it now if you want. But it boils down essentially to two different issues. One relating to what the status of zeros in numbers, and the other one relating to the rules that we have to apply when we do calculations with measurements. The status of zeros is fairly easy to line out at the beginning. Any non-zero digit is considered to be significant. So for example, if I were to measure a length of something and write down 1.25 centimeters, my significant figures would be 3. All 3 of those are significant. Note that this last digit, the 5, may not be certain, but I'm allowed to estimate its value and record it as a significant figure. Likewise, if I were to write down 252.138 grams, I would have a number with 6 significant figures, and it's important to look at that number right now and say to yourself, wow, that's a pretty precise measurement. I know I have 200, 5 tens, 2 ones, 1 tenth, 3 hundredths, and 8 thousandths. So there must be a pretty good tool that could measure the mass of something with 6 significant figures. Zeros have to be treated with caution because depending upon where they are, they may or may not be significant. For example, if I write that number, 10, I'm writing it in such a way that I have 1 significant figure. That 0 is not significant because it is written that way. If I want to declare that 0 significant, I would put a decimal point there, and in doing so would now have a number with 2 significant figures. I remind you that 0 can have some uncertainty about it, but I'm still allowed to record it as a significant figure. This puts new meaning on a number like this, 10,000, because the way I've written it there, I am in a sense declaring only 1 significant figure and saying that I know this digit with some uncertainty perhaps, but I have no information at all about any of those, and hence I write the number that way. Very different from writing this, which declares to the world that I have 5 significant figures and that I know the value of this, I know the value of that, I know the value of that, I know the value of that, and this last digit containing some uncertainty is allowed as a significant figure as a result. So you can see that decimal point becomes really, really important. These zeros here are what we call placeholders, just showing us the magnitude of this. These zeros here are in fact significant figures because we wrote the decimal point there. It works the same way for numbers that are less than 1. Here's an interesting example. Think about that 0 for a moment. That 0 there isn't really even necessary in that we could get rid of it and the number would be the same. Likewise, this 0 here is not a significant figure because it is merely telling us the magnitude of this number here, which is our only significant figure. This number has one significant figure, and this number here, of course, can contain some uncertainty in our measurement process. Interestingly, any zeros between non-zero digits are significant, meaning that this number here has 4 significant figures, or as we say colloquially, 4 sig figs, because we would have to know the number, the exact value of this and the exact value of that if we were in fact to be able to get to that 2 there. These 3 zeros here are not significant, merely placeholders, and this one here a convention that allows us to clearly locate that decimal point for, again, efficient communication. So the zeros then are going to be the only thing that really gives you problems in terms of determining the number of significant figures for a given measurement that you have. We would never throw away significant figures, but nor would we claim to have more than perhaps we really get. The problem will come when you do calculations and you discover that your calculator kicks out a number or whatever the number of significant figures there, as far as the calculator is concerned, can be virtually infinite, but we know in measurement that those are not legitimate significant figures, and you have to step in and record this value to the correct number of significant figures. Not to put too fine a point on it, then we have rules that apply to these significant figures, and there are essentially 3 sets of rules. One deals with addition and subtraction, one deals with multiplication and division, and one deals with conversion factors, which may or may not represent a special condition. And we'll look at examples of each one of those right now. For addition and subtraction, all that really matters are decimal places. And the rule is that you get in your answer however many decimal places the number with the fewest decimal places has. So in this case, the top number, 3 significant figures, the bottom number, 1 significant figure, and most importantly, only 1 decimal place. And so although the numerical answer would be what, 2.32, we're really not allowed to report that 2 because we have no information at all about what that number is there. Remember that this is a very different setting than this, where now we can in fact record 2 decimal places for that number because this is a decimal place, and as a result we can have it. Remember that we would not be allowed to write that 0 unless we had it as part of our measurement. So for addition and subtraction, it is purely related to the number of decimal places. For multiplication and division, it is related to significant figures. So if we take then 2.68 and multiply by 1.2, our numerical answer is 3.216. That's what comes out of my calculator. But notice that this number has 3 significant figures, and this number has 2 significant figures. And we are limited to the number that has the fewest. This measurement here with only 2 significant figures limits the precision of our answer, and so we have to take this number here and then round to our 2 significant figures. So it would become, in our official measurement, 3.22, whatever units it has, as the 6, which we can use to round, but we cannot record as a significant figure, changes that 3.21 into 3.22. And here then is our official answer with the correct number of significant figures, wrong number of significant figures. We're going to limit this to 2 significant figures, so that 1 then doesn't do anything to that. And so our real answer, sorry, my bad, is 3.2 centimeters. 2 significant figures here, 2 significant figures there. One more quickly, and then I'll stop, because we'll do some practice calculations in class 2. Let's say we have 2.78, we're going to divide it by 0.63. If we do that on your calculator, I get again 4.4127 to number of decimal places I have, but again here 3 significant figures, 2 significant figures. Remember that that 0 does not count. And so we only get 2 significant figures in our answer, so this 4.4127 would then be correctly recorded as 4.4, and of course whatever units we had, respecting our significant figures. We'll practice more with this in class. Finally, just a few words about errors. We're going to be doing experiments and we're going to be measuring properties, and sometimes we're going to be able to evaluate our experiment based on an error that relates to a known value. If we're trying to estimate a density or something like that for something that we already know, we can use this formula where we take the experimental value and subtract the true value and divide by the true value to give us a measurement of error in a percentage terms, so we'll know how good our experiment was and how close we came to the known value. Again, we'll give more examples of how we use this when it comes up in lab.